Welcome back, everybody. Now, like I said in the last video, we're going to start on coding this bad boy up. And what do I mean? If you're just new to this, we're going to code up the simplest possible neural network that we could think of, which is the equation for a line. And just to refresh everybody's memory, this is essentially what we're going to code up here. What you see on the screen is y equals mx plus b, excuse me. And you have an input layer here, x, some math operations as represented by these arrows happening, and then you see how close you were to the real y value which you have, and then you update those biases and weights, or in typical normal people who speak math, slope and intercept. Great. All right, and to do this, of course, we need a data set. So I want to grab some real messy data, some real world data, and given that I have a meteorology background and I come from atmospheric science and oceanography, my preferred data set is the US Climate Reference Network. And this is a really cool network that's been around for a while. It's quality controlled, it's supposed to be representing the general climate state. All right, so let's grab some of this data. I already have cleaned up data. This is just showing you where to grab it. So if you wanted to follow along, you can do the same. All right, so I like to go with the daily data. The hourly data is really nice, and even sub-hourly, which I've used in the past. But let's jump into the FTP client, excuse me. And here you can see I've clicked on 2017. Good year. Click on that. Grab any one of these text files. I'm going to search for, oops, screwed that up. Durham, North Carolina. Representing the 919. All right, here we go. So you can grab this, you can download this data set. I should not have clicked on it. That's not what I wanted to do. Anyway, I've already downloaded the data set, so don't worry about that. I did some pre-processing, so I only extracted temperature and humidity. So what we're going to have is daily temperature and humidity. All right, so if we get into here, look at the basic building blocks. I'm loading some libraries up here at the top. Basic libraries to use for processing. NumPy, pandas, seaborn to make plots look pretty, and matplotlib to do the actual plotting. So we can see this thing happening in real time. I like to set the style to white grid, just so I think it looks cool. No real reason. And here's where I'm actually reading the data set. So we're reading in the CSV file, and we're reading in temperature and humidity. Like I said, I did a little bit of pre-processing. That was with a bash script. If you'd like to see that, just hit me up in the comments. I'll tell you about it. And again, recall that this is all we're going to do right here. So before we move on, I think it's good to look and visualize your data and visualize actually our target. So the nice part about Seaborn is that it'll plot the regression line for us. And that's what I'm doing right here. All right, plot show. Save that. Yes, I know I used Emacs for all you Vim haters out there. And I'm going to keep using Emacs because that's what I do. All right, let's see, what did I call this? Part 1. Okay, oh, our graph's over here in the corner. Pull that over. So this, you have temperature in Celsius on the x-axis, and you have relative humidity on the y. And here's the line we're going to be trying to fit here. And you can see just how messy this data, real-world data, can be. Now, I mean, of course, looking at this thing, you probably wouldn't be like, let's fit a line through. That's a smart idea. You'd probably look at this thing and say, oh, I probably need to split it up by season, or have some other way, or maybe there's a third variable here, which there is. Specific humidity, for all those interested, would be a good variable to add to this. But in our case, let's keep it simple. Temperature on the x-axis, and we're going to try to estimate relative humidity given temperature. So in our paradigm, if we were to write this thing out, we would have RH equals m times T plus B. So we're assuming that there's an equation here for a line, and we're going to try to figure out what this m and b are, this slope and this intercept. All right, let's cancel out of this guy. All right, to start out, I'm going to go interactive mode. So for those of you who don't know, matplotlib offers a nice interactive mode, so you don't have to keep typing in plot show, and you're going to see why I did this in a little bit. But getting back to the neural network part, what we want to do is fit the line. So let's start out by just defining it as x. Temperature is x, and I'm just going to grab the values out of this and flat, just to make sure it's a flat array. And then there's the real y values. Going back to the nomenclature we use. Oops. RH. is it values? Values, yeah, values, flatten. And all I'm doing here is grabbing the data from the data frame. Let's say this is a pandas data frame. And then flattening it to make it just one-dimensional. All right. Then we're just going to take some random guess of the slope. Slope equals, let's say, 5. I don't know if that's real. I don't care. Doesn't really matter. Doesn't really matter what you pick here, because you're just taking a random guess. And the beauty of it is that the neural network will update itself. Now, typically, you wouldn't do some of the stuff I'm doing right now. This is just to illustrate the point and show you how it looks. All right, and let's pick an intercept also of, I don't know, 3.5. It doesn't really matter, like I said. So just take some random guesses in here, and then you want to calculate the error. Oops. We'll say y. Before you calculate the error, you got to calculate the guess, of course. And your guess is just going to be your x times your slope. Or actually, probably I'll write it like mx plus b. Slope times x, which is just your temperature, plus the very verbosely written intercept. Let's put that in here. Boom. What's our error? It's y real minus y, gosh dang it, y guess. And just for good measure, this is the mean squared error. So we have that measure error, and we're going to square it. Let's put that closer together. I don't like that. Okay. So here's just one iteration. And now we have to have some way. Okay, we made a guess. And like you remember from the chart, actually, let me pull that up while we're talking here. There we go. If you remember from this diagram we showed in the intro, what you're doing here, we've completed these steps. We've taken this guess. We've calculated this error. Now we need to do this updating. Now what I skipped over in the last introduction was what this update actually is. And it is the change in error given these parameters. So for those of you who are calculus oriented, you can check out some of the videos on that. If you'd like, I can do a specific video that describes the calculus behind that if you'd like. And of course I would love to do that because I think it's super cool and incredibly fascinating how a simple equation like this can actually update you in the right direction. So if you want, just let me know and I'll do something on that. All right, going back to the code, we're going to be doing this updating. And all this update is saying is that the change in the error with respect to the slope, for example. And the way this is done is you take a look at the error function here. Our error function is this squared error. So here I did the mean of the squared error. Really it should be squared error. And when you take the derivative of the error with respect to this slope value, what you get is an equation. I'll do the mean. I'm going to do the mean eventually. What you get is this inside equation. 2 times the error times x. That's for the slope. And just to give you a little bit of intuition before I move on here about what this means. I knew I said I wasn't going to go into the calculus, but I can't help it. The little intuition here is this 2, when you take the derivative of something that has an exponent, you take that exponent, throw it in the front, and you subtract this exponent by 1. So that's the first part. And then you got to do the inside because you're actually after this slope value. So the error here depends on the slope. And we know that the slope itself is sensitive to changes in x. So that's just to give you a brief intuition about where these numbers come from. They just come out of the air. All right, and we can do the same for the intercept. So we want to update both the slope and the intercept. I'm just going to type it inter. 2 times the error. Now note here I didn't put an x. And why is that? Well, they both of them are related. The error is related to both the intercept and the slope, but the difference is the intercept is not sensitive to changes in x. So I don't have an x there. All right, and that's the basic intuition. Then all I have to do is update the actual slopes. Go straight and mutable. I'm going to write this out completely, even though plus change error with respect to slope. And we'll do the same for the intercept. Error with respect to intercept. All right. Now you may have seen these equations before. If you've followed any machine learning videos, you've probably seen these written as the gradients, right? And if you notice something that I don't have here, it's a learning rate. So this learning rate determines how much I should change the slope and intercept given this gradient. So the cool part is we could just throw it over here. Here's our learning rate, LR. I haven't defined it yet, but let's define one up here. When we're defining all these initial conditions, we'll define a learning rate. 0.001. I picked 0.001 for a reason. I'm not going to tell you yet, though. All right. And obviously, when we update it, we want to continue to do this over and over and over and over again. You know, this is what neural networks do. We take one guess, we check it. The change in error with respect to the slope and the intercept tell us which way to go. But we don't want to take enormous steps in that direction because we may skip right over the answer that we want. So this is where the learning rate comes in to say, okay, slow it down. It's kind of like if you know your destination and you accelerate really fast towards where you're going. Well, you don't want to accelerate too fast because you actually might pass your destination. So this is a way of slowing down that process so that you can meet exactly the point where you want to go. And in this case, we're trying to minimize the error. So we're trying to get as little error possible in our guesses. So we guess the y. We have a real value of y that we know, and we're trying to minimize that error. And we don't want to overshoot. So this is where this learning rate comes from. All right, so we can put this all in a big loop. And I'll call this I in range box. Let's do it like that. Boom, boom, boom. All right, awesome. We need to define epochs. Let's go for 100 for now. And we want to see our progress here. So this is where we're going to replot what I plotted up there. So this is the temperature, the real temperature and the real relative humidity, so we can see our target. And below it, I'm going to plot what we have learned. So the x is still the same because that is not what we're trying to guess. This is our input. Our input's the same. But now we take our input, multiply it by our guessed slope, what we think the slope is, and our intercept. And we're going to make this line black so that we can see it. So the other one was... All right, and let's make sure that the axes don't change a bunch. I think I do it this way. Let's try that. So minus 10 to 40, that should be an acceptable range in temperature. Humidity probably is in that range, 0 to 100. Excuse me. And we want to make sure this thing pauses for a second so we can actually see it as it loops through. And I think it's like that. Clear the axes. I think that should be right. We'll give that a try. All right, so as you can see, there's not much code here, but what I'm doing at the bottom here is plotting so we can check the progress of our learning. Let's take a look at this thing as it goes. Let's run it. Let's hope it works. No errors. Ah! Did I not define it? Oh, I felt it change an intercept. Change an inter. Some astute watchers hopefully caught that. Here we go. Let's try it again. Boom! And it died. Int has no length. Uh-oh. Did I update I? Intercept here. I. Uh-oh, what did I screw up here? Int has no length. What am I trying to figure length of? Let's take a look at this statement. Oh. I think I'm supposed to put this in brackets maybe? I put it as a list, so it's not a tuple. Oh, let's try that again. Alright, errors are natural. We'll give that another shot. There we go. Actually, you can't even see it on the screen. So you can see this black line here is the one that we are learning. And you can't see it, it's kind of going really, really slow, but it's gradually making its way in certain directions. It's kind of teetering and tottering. Keep your eye very close to the black line. It's supposed to be converging. Oh God, what happened? Oh, I ran out of epochs. If this keeps going, let me keep on running that. Let's put it for a lot of epochs here. Go 1,000. Okay, let's bring that back. Bring that back, bring that back. Here we go. Okay, so the thing is training. It's really boring. I mean, it's a line to begin with, but it's converging really slowly. Now I've picked a really small learning rate, and there's a reason why I did that. So over time, this black line will actually eventually, and it's going to take a while. I think when I did this before, it took like 10 minutes or so, maybe 5 minutes to actually get there at this slow learning rate. But there's a bunch of tricks we can do to accelerate this. So we don't have to sit there and stare at this line and be like, oh God, why is it going so slow? Well, one thing you might want to try is increasing the learning rate. But we will see what happens when I pop that over to something higher than 0.001. So let's say I bumped up that learning rate. God, no, be quiet. Here, stop you. Stop it. Here, stop it. There we go. Okay, so let's say I did this to, not even a lot, let's say I went to 0.05. And we're going to do this quickly. Let's see what happens to the line. So this is the same code, haven't changed a thing. All I did was change the learning rate. And remember, the learning rate, it just shows, it tells how big of a step you're going to take in the direction given that gradient. So let's take a look at what happens. All right, you didn't see it because it was kind of off the screen, unfortunately. But the line started out somewhere over here, and then it starts jumping around, and now you have this completely wrong answer that's never going to converge. And there's a reason for this, is because there's some instabilities here. And real quick, to help you understand this, is there are strategies that you know and have employed in the past. If you've done any any neural networks with Keras or TensorFlow or whatever, before you use any data set, usually you do things like normalize and scale the data. And that is related also to helping out with stability and getting to the answer faster and better. So I'm going to stop this for now. And in part 2 here, we're going to do exactly that. We're going to standardize the data so that it fits, it learns a lot faster, and you'll see how that works. And we have to go for fewer epochs. And then we're going to start adding layers. So here I have just one neuron, right? Just one layer. I'm going output. Then I have only 2 parameters. And we're going to add another one after that in the next part, after we do the normalizations. And then eventually we're going to add an activation function in here and see what nonlinearity looks like. And then I think I'm going to go and do the same kind of linear example, probably in Keras and TensorFlow, to just give you a flavor for what that looks like. All right, cool. If you liked what you saw, please give me a thumbs up. And if you have any questions, definitely leave them in the comments and hit me up. All right, I'll talk to you guys later.